Okay, so welcome to the course in commutative algebra. We will start with basic ring theory, where we will do some basics of ideals, operations on ideals, extension, contraction and so on, and then we will move on to module theory. Again, we will begin with the basics and try to study various aspects of basic module theory, and then we will move on to localization, integral dependence, and going down theorems. We will then move on to chain conditions, Noetherian rings, so this is one of the most important classes of rings in commutative algebra called Noetherian rings. Some properties in Noetherian rings, some important properties such as primary decomposition, and we will then study Artinian rings and Hilbert's null-Stellenza. Depending on time availability, we will do little more in this direction about Artinian rings and something about graded rings. Okay, so this is a rough structure of the course. I will be following the book Introduction to Commutative Algebra by Michael Atiyah and I.G. MacDonald. So, approximately 8 chapters of this book, along with some portions probably from outside, but I will mention that when we go along. Okay. So, let us begin. I hope you all had a basic course in ring theory. So, today it will mostly be recalling the basic concepts from your algebra 1 first course in algebra. So, a ring A is a set with 2 binary operations. So, called addition and multiplication and multiplication. such that what are the properties? The ring with addition A with addition is an abelian group, and then the multiplication is associative and is distributive over the addition. So, our course is commutative algebra. So, therefore, we will be dealing with rings which are commutative, or in other words, we will have throughout this course we will have two more hypotheses to the set of all these set of hypotheses for rings, that for x comma y in A, x y is equal to y x, and I will also assume that our rings contain the identity element. There exists multiplicative identity, that is, there exists an element called denoted by 1a such that is satisfied. So, our rings will contain multiplicative identity, all rings will have multiplicative identity, commutative rings with identity. If you have doubts, you can stop me and ask me. Let us look at, I am sure you have seen many examples. Some basic examples are tell me some basic examples. Z, R, C. So, you missed something in between, Q, then. So, we should always start with the 0th example. It should be, what should be the 0th example? What about this? Simply 0. This is a ring. So, this is a ring with, so this also is a commutative ring with multiplicative identity where 1 of A is equal to 0 itself. Okay. So, therefore, this is, and this we will denote this by 0 ring. A is called the 0 ring. Okay. So, these are all standard examples that you must have seen. Now, if this is 1, I should say this is 2. If A is a ring, then A is a commutative ring, then Ax is. You understand this notation? This is set of all A naught plus A1 x plus etcetera A n x power n, n in n and AI in R. Collection of all polynomials, and this has a natural addition and multiplication that you have seen, you must have seen in your earlier courses. In the similar manner, one can define polynomial ring in many variables. So, this will be collection of all, I will write the compact notation A I1 to I n x1 power I1 x n power I n such that I j belongs to n. So, here my n contains 0. I assume that the natural numbers contain 0 and A I belongs to A. Okay. So, this is these are some again standard examples of commutative rings. Another collection of nice examples come from set of all functions. If I have S be any set, then set of all functions on S, set of all functions from S to R. You can define an addition and multiplication on this ring. How do you define an addition? Pointwise addition. Pointwise addition. So, I can define f plus g acting on an element x. By definition, this should be f x plus g x, and similarly f g acting on x is f x times g x. With this addition and multiplication, this is a commutative ring with identity. So, once you define rings, once you think about some natural examples, the first thing that one does is to think about the substructures. So, you have a ring. So, then what are the subrings? When do you say a subset is a subring? A, so let A be a ring, a subset B contained in A is a subring if B itself is a ring with respect to the same binary operations on A. With respect to same binary operations, B is also a ring. Then we say B is a subring of A. So, here for the definition, we do not need a subring to contain the identity element. Okay. It is our convention that our rings contain identity element. Okay. In this course, all our rings contain identity element, but in the subring case, we do not insist that. When we are talking about a subring, we are not insisting that subring contains the multiplicative identity. Okay. I will come to the reason why we are not very strict about it. I will come back to that a little later. So, quickly some examples of subrings. This, so if I just replace this, okay, let it be here. Some examples. All of them are subrings of C. right. And for can you tell me a subring of Rx where R is a ring, or let me denote it by A itself is a subring of Ax. Another subring, can you tell me another subring which is maybe slightly bigger than A? Any subring of A will be a subring of Ax, but can you tell me a ring which is bigger than A and contained in Ax and which is a subring?
With constant term G.
Polynomials with, so I will denote this by, let us say A1 set of all Px in Ax such that constant term of Px is 0. So, if you the natural addition and multiplication, if you do that, if you take two constant polynomials with no constant term, you add and multiply the, it is going to remain another polynomial in the same set, because it cannot have a constant term by the usual addition and multiplication of polynomials. Okay, so we will see more examples later. Sorry?
Polynomial with even parts.
So, even when you talk about polynomials with even coefficients, you are talking about z maybe even even powers, yeah. So, that is, yes. So, this is are you talking about a naught plus a1 x square a2 x power 4 plus a n x power 2n, is this what you have in mind? Yes. So, a I in A. So, this ring is usually denoted by a x square, that is another subring. We will see more and more examples of subrings as we go along. So, now let us move on to another important aspect of ring theory, that homomorphisms. So, a map F from A to B, where A and B are rings, is said to be a homomorphism, to be a ring homomorphism if, what are the properties? If f of x plus, so for all x comma y in A, f of x plus y should be equal to f of x plus f of y, and for all x comma y in A, f of x y should be equal to f x times f y. Then if a map satisfies these two properties, then it is called a ring homomorphism. Now, if A contains a multiplicative identity, so in the for the purpose of our course, all our rings are commutative and it contains the multiplicative identity. So, if 1A is there, then what can you say about f of 1A? This will be 1 of B. So, this is partially true. This should be 1 of f of it should be a multiplicative identity of the image. For that we need to say something slightly more, that this is indeed a ring or a subring. So, first observation is that if image of F is a subring of B, okay, and there is another object which is associated with the homomorphism, which is kernel of F. This is all elements in A such that F of A is 0, and observation 2 is that kernel F is a subring of A. Yes, identity of subring need not necessarily be the identity of the bigger ring. One can think about an example. I'll
So, but if operations are same, how can we identify?
well, first of all, the subring need not contain the identity element. For example, in Z6, okay, if you look at the ideal, if you look at the set 0, 3, okay, this is a subring of Z6, right. Now, what can you say about 3? 3 times 3 is 3, and 3 times 0 is 0. So, therefore, this is multiplicative identity of this is multiplicative identity of the subring. If I denote this by B, B is a subring of Z6, and okay, these are all dependent on conventions. I can even say that my subring contains all my subrings. A set is a subring if it contains 1, and I can say that F is a homomorphism if F of 1 is equal to 1. But I won't no, I am not doing that in this course. It depends on the need of the development of the course. One can set various conventions. So, in this I do not do that. There are books which follow this convention as well as the convention that we are using here. So, okay. So, this is kernel and image are subrings. Now, we have a slightly more general object which are called ideals. A subset I in A is an ideal of A if there exists if I plus is an abelian group, and for every A in A and X in I, Ax is in I. If I satisfies these two conditions, then we say that I is an ideal. So, I guess we know many examples of ideals in all these rings. For example, Okay, so what should be the zeroth example? If I take any ring A, yeah, the set 0, this is an ideal. Okay, and in Z we have NZ, these are examples. What are the ideals of Q? What are the ideals of Q? 0 is already there, yes. Any other ideal? 0 and Q itself. So, another example here is A is an ideal of A itself. The whole ring is an ideal because it obviously satisfies both the conditions. So, therefore, this and Q. Now, in AX, can you give me an example of an ideal? Yeah. So, ideal generated by X, what does that mean? Which means I say I look at all the collections X dot Px where Px is in Ax. So, this is something that we have seen just few minutes back. What is this ideal or what is this set? We saw a different representation. Polynomials with constant term 0. Okay. Now, we had another example, f of s. Can you give me an example of an ideal in f of s? Set of constant functions, will it be an ideal? Right. If I take see, it should satisfy, I take any element in this ring, multiply with the set, multiply with the element, it should again be in this.
Take a subset, finite subset.
Yeah. So, take a non-empty subset, let us say x non-empty subset of x, and look at this collection I of x to be set of all f in fs such that f of x is 0 for every x in x. Okay. So, this is I want you to check that this is indeed an ideal. Okay. Now, so this is let us go back to what we wrote here. Kernel is a subring, and one can, this is again another easy exercise. If f from A to B is a ring homomorphism, then kernel of f is an ideal of A. Okay. Again, this is something that you must have done in your first course. Now, once we have the concept of ideal, that gives us an equivalence relation, that is I can define an equivalence relation A related to B if and only if A minus B is in I. The collection of all equivalence classes of this relation, this is an equivalence relation and the collection of all equivalence classes is denoted by A mod I is called the quotient of A with respect to I. So, in our situation I is an ideal in a commutative ring. So, this there is a natural addition and multiplication defined on A, which is inherited from natural addition and multiplication defined on A mod I, which is inherited from A, which is A plus I plus B plus I to be equal to A plus B plus I and A plus I times B plus I defined to be A B plus I. This natural definition of addition and multiplication gives a ring structure to A mod I is a commutative ring with identity with respect to the above binary operations. First of all, we have a natural map from A to A mod I. There is a natural map there exists a natural map phi from A to A mod I. What should be the natural map? Phi of A equal to A plus I, the equivalence classes which A belongs to, and then phi is, so phi is not simply a map, but it is a ring homomorphism. And slightly more, this is a, yes, phi is a surjective ring homomorphism. If I have, if f from A to B is a ring homomorphism, so this is called isomorphism theorem. This says that if this is A to B is a ring homomorphism, then image of f is isomorphic to A mod kernel of f. This is something that you have seen in linear algebra, group theory, and possible in your ring theory course as well. Linear algebra, this theorem has a nice name. What is that? Rank nullity theorem. The rank nullity theorem is precisely this. It is the first isomorphism theorem of vector space. Vector spaces. Okay, so let us look at the quotients, see when you have a you have a ring obtained from A by doing an operation. Okay, we are going modulo. So I have a ring A, I have a ring A mod I. One of the natural questions to think about is what are the ideals, in A mod I. Okay, so this is again explained by this, looking at the ring homomorphism, natural ring homomorphism. One can immediately obtain explicit expression of explicit description of all the ideals of A mod I. So what are the ideals of A mod I? Are precisely are in 1-1 correspondence, correspondence with the ideals of A containing I. So if you take any ideal here, its inverse image will contain I. Why is it so? Why is the image, so if I take 0 is there in the ideal, in any ideal. So if you take the inverse image, phi inverse of 0 is always there in the inverse image. Now phi inverse of 0 is nothing but I. So therefore I is always contained in inverse images of ideals here, and you can see that if you take any ideal here, its image will be an ideal in A mod I. So that poses a question, what can you say about ideals if I have a ring homomorphism from A to B, okay, and I have I is an ideal. Is it true that f of I is an ideal in B? Is it true? No. Can you give me a quick example? Z to Q identity map. Nz is mapped to Nz, but Nz is not an ideal in Q. The only ideals of Q are either 0 or the whole of Q. But now let us ask another question. If J in B is an ideal, then what about F inverse of J? This is indeed an ideal. So the answer is yes. If you have not done this verification, one can do it. Now let us look at another set of definitions. An element x in A is a zero-divisor if there exists a non-zero element B in A such that x y is 0, or in other words x divides 0. So there exists an element y with the property that x y is 0. So let me just give 3 definitions. An element in an x in A is a nilpotent if there exists n bigger than or equal to 1 such that x power n is 0, and an element x in A is a unit if there exists y in A such that x y is 1. These are three classes of elements. Well, there are elements which are neither a non-zero divisor nor nilpotent nor a unit, but these are some important classes of elements. So, some quick examples. Have you seen examples of zero divisors in Z6? What are the elements? 2, 3 are zero divisors. One more important example of a zero divisor is in any ring 0 itself, right. So, that should be the 0th example. 0 is a zero divisor. Okay. So, by convention we do not talk about zero divisors in a non-zero in a zero ring. In a zero ring 0 is not really a zero divisor because this is not satisfied, there does not exist a non-zero element. So, it cannot be a zero divisor. Okay. Some examples of nilpotent elements. Can you give me an example of nilpotent element in some ring? Something similar. Can you cook up an example of a nilpotent element in Z mod Z4 and 2, right. 2 square is 4. So, this is in Z4, this is nilpotent. Of course, you have seen units, you take any non-zero element in a field, it is a unit. Non-zero elements of a field, any non-zero element of a field. Now, do you see some relation between these three? Nilpotent is always a zero divisor. So, is a zero divisor, but the converse is not true right here. 2 and 3 both of them. 3 square is 3, 3 cube is 3, 3 power 4 is 3. So, therefore, 3 power n is never 0. So, this is not a nilpotent. And can you see some relation between 3 and these two? Sorry? Yeah. So, if you take the collection of all zero divisors, this is contained in this set. This and this sets are disjoint, right. Collection of all units and collection of all zero divisors are disjoint sets.